Let us pick up where we left off yesterday, which is a journey into the Schwarzschild horizon. We said that inside for r less than rg, the dt squared terms becomes negative and the dr squared term becomes positive. Therefore, the time coordinate becomes space-like, and then the r coordinate becomes time-like. Their roles get interchanged. And so we can't really extend this coordinate system inside the event horizon. So we said, let us construct a coordinate system which is attached to a freely falling material particle. You could also do it for photons, as Eddington did, but we stuck to material particles. And that was done by Lemaitre in 1933. And the choice of coordinates he made is that for time, he will use the proper time of the free-falling particle. And for the coordinate r, he will use the coordinate r1 we had written before of the freely falling particle. But it turns out that for matter of convenience, it is better to define the new coordinate as capital R, which is related to our Schwarzschild coordinate r by this relation. Now you may wonder, where did such crazy combinations come from? These are the kind of substitutions that Chandrasekhar used to do all his life. You will remember that that sort of a structure we saw for a proper time taken by a particle to fall from distance r1 to a distance r. Okay, so that particular structure is intimately related to the combination of r and t we had for a freely falling particle. Okay, so Lemaitre didn't pull it out of thin air. Now let us try to understand properties of this. First thing to appreciate is that the Schwarzschild radius rg corresponds in the new coordinates capital R and tau to 3 by 2 r minus c tau. Okay, rg is replaced by that. So you will find that at r equal to rg, the old Schwarzschild coordinate had a singularity, but here at rg, none of the metric coefficients or their derivatives have any singularity whatsoever. The only singularity of this metric occurs when r is equal to c tau, which corresponds to r equal to 0, which is a true space-time singularity. Please notice that this metric is stationary, but tau enters explicitly in the metric, whereas time did not enter explicitly in the Schwarzschild metric. Now we want to make a little plots. So that is what I have done. We have already dealt with this. Yes, this also I've already said, that r is equal to c tau, which corresponds to our old small r equal to 0. There is a true space-time singularity, and the curvature goes to infinity. Now, each falling body with r is equal to constant, remember the coordinate of the body is now attached to the body, so that remains a constant. So r equal to constant, you'll find, corresponds to moving to smaller and smaller radial coordinate r, the Schwarzschild coordinate. And the whirl lines of radial light can be found from the condition ds is equal to 0, d theta and d phi are equal to 0. So now let me translate all these formulae into simple figures, okay? And that should stay in your mind. So let us be very clear about what we are plotting. The vertical axis is the proper time tau, and this is our coordinate r. So the two axes are the coordinates of the Lemaitre coordinate system. Now, the whirl lines of the particle corresponding to the freely falling particle are r is equal to constant. So lines of constant R, these vertical lines, are the whirl lines of freely falling particles. And what you find is the following. If I send a light signal, then the equation of motion for light can be obtained very simply by setting ds is equal to 0, as I said, d theta and d phi equal to 0. Then if you simplify that, you will find c d tau by d capital R is equal to plus or minus square root of rg over r. In other words, what we are saying is that the slope of these lines which define the outer boundary of the light cone are given by square root of rg over r. So if r is smaller than rg, then this is greater than 1. If r is greater than rg, this is less than 1. And when r is equal to rg, this is equal to 1. So now let us look at this trajectory properly. For a given value of r, our old coordinate, for a given value of r, for a given value of r, there corresponds whirl lines which is c r minus c tau is equal to constant. The whirl lines are r minus c tau is equal to constant. So what I have plotted are various whirl lines corresponding to various values of a Schwarzschild coordinate r. And what you see is that for r greater than rg, take this yellow line, whirl line, c dr, d tau dr is less than 1, and the whirl line is time-like. It's inside the light cone. At precisely r is equal to rg, the whirl line is null. It is gracing, it is tangent to the light cone. Inside r is equal to rg, the whirl lines, which are our old coordinates r, are space-like because they're outside the light cone. This is what we meant by saying r and t have interchanged their role. But you notice the very fundamental message from this picture is that if you are in a freely falling particle, capital R is equal to constant, you are moving inexorably towards smaller and smaller small r till you finally hit the singularity at r is equal to 0. Okay. So now this behavior of the light cones can be represented by this diagram, which is a diagram originally due to Roger Penrose. Let us imagine we emit a flash of light at that point, far away from the black hole. The wavefront will be spherical, and the point of emission will be at the center of the spherical wavefront. It's not at the center there because moving the points in PowerPoint is quantized, so you can't get it exactly in the center. Now, if I emit the signal closer and closer to the black hole, you see very clearly the gravitational deflection of light. So at short distances from the event horizon, the wavefront surface is displaced by the strong gravity. The wavefront is still a spherical wavefront, but with respect to the point of emission, it is displaced. At precisely the horizon, if I emit a flash of light, the spherical wavefront touches the horizon internally. There is no part of the wavefront which is outside the horizon. Now, if I emit a flash of light inside the horizon, no matter where I am inside the horizon, the expanding wavefront detaches itself from the point of emission, and the light is pulled towards the center of the black hole, which is where the space-time singularity is. So this very simple picture captures all those complicated lines in the previous graph that I had shown you. Yes. So, all plotted in the way Roger Penrose himself plotted, these are beautiful diagrams. He thinks everything is, his thought process is geometrical. So here is our collapsing star in 2 dimensions. And you notice, and this is the Schwarzschild radius. That cylinder is the Schwarzschild sphere stretched in time. So you see the tipping of the wavefront till finally at the Schwarzschild radius, as we said, C d tau by dr is equal to 1. And after that, the wavefronts tip towards the singularity. Okay? All right. 1916 January or February was Schwarzschild's exact solution of Einstein's equation. And one had to wait a very long time. In 1963, the paper itself appeared in the journal in 1964, when the New Zealand mathematician Roy Kerr discovered the exact solution for the geometry of space-time around a rotating star. It wasn't considering a black hole, but a rotating star. Now, you would expect such a metric to be stationary and axially symmetric. And it is. Now, I've written the metric for you in all its glory, but let us now discuss this metric mainly in the equatorial plane. Please remember that if I am dealing with a Schwarzschild black hole, because of spherical symmetry, any plane that goes through the center is equivalent, whereas because of rotation, there's one plane which is different, so let's stick to that equatorial plane. So I will only write formulae where here we put theta equal to pi by 2. And one introduces the angular momentum parameter A, which is the ratio of the angular momentum to the mass. And that will play a very important role. Now, as you will see, for a black hole of a given mass, there is a maximum possible value for the angular momentum, A max. You'll see what that A max is in a minute. And a black hole with that angular momentum, maximum possible angular momentum, is referred to as the extreme Kerr black hole. These are all things that are very relevant in the context of mergers of black holes. So here is the Kerr metric on the top in the equatorial plane. And I have only written the important terms in full, the rest are all dots, but you have the full formula, please write it down. For comparison, you have the Schwarzschild metric over here. You notice 2 important differences. One is that the curvature term is different. And secondly, the appearance of dt d phi. Now, let's go back to the Schwarzschild metric, which I have written in full here. At the horizon, at the Schwarzschild horizon, the coefficient of the dr squared term goes to infinity. At r is equal to 2gm by c squared. But you notice that precisely at that distance, the coefficient of the dt squared term also goes to 0. But this case for the metric, obviously you would, the place where this goes to infinity is going to be different from where this goes to infinity. And because of that, a very new, interesting, and exciting feature appears in the Kerr black hole. Now, let us consider a maximally rotating black hole. You find that let me write down this formula because it's not, I notice it's not in the slide. I don't see why it's not in the slide. But what we'll be dealing with G00 going to 0 and G11 going to infinity. Now, you'll find, if you now take the theta is equal to pi by 2, you'll find that there are two surfaces. The first surface is oblate, and the other one is spherical, and they meet at the poles. This distance from the center is our gravitational radius, or the old Schwarzschild radius, 2gm by c squared. And this distance is half of that. Let's look at this same picture from above the equator. So what we will see are two circles in the equatorial plane. This outer circle, where the coefficient of dt squared term goes to 0, is known as the static limit. You'll see why in a minute. This inner circle at half the gravitational radius, where the coefficient of dr squared goes to infinity, is our good old horizon. You notice that these two surfaces are not coincident like in the Schwarzschild case. The region in between is referred to as ergosphere. And this is the direction of the spin of the black hole. Now, what is the essential new feature that occurs at this static limit already? We know that inside the horizon is going to be very similar to Schwarzschild horizon, except there is rotation in this case. So let us recall the properties inside the Schwarzschild horizon, which is the outer radius, Rg in our case. So inside the Schwarzschild horizons, particles and light cannot be at rest with respect to infinity. We saw that in the Lemaitre coordinates. R is equal to constant is not allowed. Particles and light have to move radially towards the central singularity. And the second feature, which we saw yesterday, is as seen by a distant observer, it will take an infinite time for the particle to reach the Schwarzschild radius, which in this case is also the event horizon. Okay, now let us see what are the properties in the Kerr case. Inside this ergosphere, you are inside Rg, the same Rg, phi equal to constant is not possible. In other words, a particle has to necessarily move. Particles and light must rotate around the axis of symmetry. R equal to constant is possible for particles and light inside the ergosphere. So a particle or a photon can choose to be in an orbit inside the ergosphere, even though it's inside Rg. Rg is not the horizon, please remember. But the interesting thing is they can come out. So the surface of the ergosphere is not a semi-permeable membrane. You can go in, you have a multiple entry visa. You can go in and come out, which you can't do for this. Now, particles can reach the ergosphere as seen by us. The particle can reach the ergosphere in finite time. It won't take infinite time. Except at the poles, because at the poles, this surface touches the Schwarzschild horizon, so it will take infinite time. So if you're not particular about reaching the poles of the ergosphere, then you can do that in a finite time. Now, here are the expanding wavefronts, Penrose's diagram once again, but this time around a rotating black hole, and this red region is the ergosphere, and this is the horizon. So you see, in addition to light being pulled towards the black hole, you find that there is a shear. So if I emit a flash of light precisely at the surface of the ergosphere, this picture is wrong. It should be entirely inside, like here. But you notice that there is a shear. Now, here is a computer simulation of what a photon will do. I have, this is my Kerr black hole. And this is the surface of the ergosphere, 1 Schwarzschild radius. No, this is half. This is the horizon. This is RG. This is RG. This is in units of. It doesn't matter. There's some crazy dimensional unit. That's why I've drawn this dashed line. That is RG. That is RG. That is half RG. That is half RG. Okay, fine. So if I send in a ray of light radially with no angular momentum, as it comes closer and closer to the Kerr black hole, it will start moving away from the black hole because space itself is being dragging of inertial frame due to this dt d phi term. So the photon is dragged like in a whirlpool in water. Excuse me. And this photon will then spiral in to the black hole. Okay? So initially the stone will have, or photon will have 0 angular momentum, but a faraway observer will see the stone spiral in. So here is an example of angular motion without angular momentum. We did not give any angular momentum to the particle or photon. But its angular motion is by virtue of the dragging of the inertial frame. Now, something very interesting can happen in principle inside the ergosphere, and this was pointed out by Roger Penrose a long time ago, more than 50 years ago. It is easy to show that negative energy states can exist inside the ergosphere. Remember, negative energy states can exist inside the horizon, Schwarzschild horizon too. There is no difficulty. But here, negative energy states can exist inside the ergosphere. But ergosphere is different from the horizon in the sense that I can go in and come out. So in principle, I can do something terribly clever. Imagine there is a particle with a positive energy, because outside the ergosphere, in our world, only particles with positive energy can exist. It goes in, and having gone in, it decides to divide itself into 2 particles. One of it has a positive energy, this green one, and one has a negative energy. The negative energy particle cannot come out. It can go into some orbit for a while, or it can go into the horizon as it pleases, but the positive energy particle can certainly come out. And when the positive energy particle comes out, it will have a greater energy than when it went in, because it has created a negative energy particle. Okay? This is called as Penrose process. Whether or not this is important or interesting in an astrophysical context is a matter of debate, because you notice that some very exotic processes have to take place before you can extract energy. But nevertheless, it is a terribly clever idea, like all of Roger Penrose's ideas. Now, what's inside a black hole? Well, there is nothing inside a black hole. Okay. And this was noticed already in Oppenheimer-Schneider's calculation, but for some reason they were very silent on it. Perhaps because it offended the philosophical sensibilities of Robert Oppenheimer to find a singularity there. But it was all there in their calculation. Now, it's very clear in Oppenheimer and Snyder's paper, after creating the black hole, the spherical star continues imploding to infinite density and zero volume, whereupon it creates and merges into a space-time singularity. Now, everyone believed that this singularity is a manifestation of spherically symmetric collapse. So now I move on to developments post-1960, the golden age of black holes. The first important discovery was by Roger Penrose in 1964, when he proved a very powerful singularity theorem, according to which every black hole must have a singularity inside it. Now, the reason why this was a profoundly important discovery is that this was a statement with sweeping power. It did not deal with idealized imploding stars. It did not assume that the deformations of the stars are small. As Kip Thorne has said, it dealt with every possible imploding star that is imaginable. It dealt with the real stars in the universe because he used topological methods, okay? So the statement is, every black hole must have a singularity inside it. Now, Roger Penrose wondered whether in extreme situations this singularity can occur outside the event horizon or outside the trapped surface. So he spent 4 or 5 years, that's a lot of time for a very powerful mind like Roger Penrose, to find an example of a singularity that occurs outside the black hole. He couldn't find it, but that's not to say that there is a rigorous theorem. So in 1969, he asserted that such naked singularities, namely the space-time singularity occurring outside the event horizon, is not possible, and he stated the following cosmic censorship principle. No imploding object can ever form a naked singularity. If a singularity is formed, it must be clothed by a black hole horizon so that no one in the external universe can see it. This theorem is yet to be proved in a rigorous manner. Sounds very plausible, but as you'll see, there are important consequences of this. The next important watershed occurred in 1968 when Brandon Carter, who was a classmate of Stephen Hawking, working with Dennis Sharma, proved a very profoundly important mathematical theorem in which he showed in an exact manner that the Kerr solution represented not just one special type of a spinning black hole, but every spinning black hole that can possibly exist. So this was an extremely important development. And then, in the period between 1968 and 1972, a series of very interesting and exciting and rigorous mathematical theorems were proved about black holes, which went under the name of 4 laws of black hole mechanics. The 0th law of black hole mechanics states that the surface gravity kappa of a stationary black hole is constant over the horizon. Surface gravity is the equivalent of gm over r squared, small g, okay? The first law of black hole mechanics says that any 2 neighboring solutions containing black holes are related by the relation delta m is equal to kappa over 8 pi, delta a plus omega times delta j. J is the angular momentum, omega is the angular velocity, and a is the surface area of the black hole. Now you'll remember the wording of the 0th law of thermodynamics. If a body is in thermodynamic equilibrium, the temperature must be same everywhere in the body. You will also remember the first law of thermodynamics, which says du is equal to TdS plus PdV. And this rings a bell, doesn't it? So if you identify these two, then you see that the surface gravity kappa is the analog of the temperature in thermodynamics, and the surface area of the black hole, A, is analogous of entropy in thermodynamics. Okay. These are merely analogies, but you will see that they could be more than analogy. The second law of thermodynamics says that the area of a black hole can never decrease. In other words, if two black holes can merge and create a new black hole whose surface area is greater than that, but a black hole cannot fissure into two smaller area black holes. Okay? Therefore, again, this reminds us of the second law of thermodynamics, which says that in equilibrium, the entropy of the system can never decrease. It must only increase. So that's suggestive that one should identify the area of the black hole with the entropy of a black hole if such a concept is meaningful. And then the third law of black hole mechanics says that it is impossible by any process, no matter how idealized, to reduce the surface gravity kappa to zero by a finite sequence of temperatures. The third law of thermodynamics says it's impossible by any process, no matter how idealized, to reduce the temperature of a body to the absolute zero of temperature by a finite sequence of operation. Obviously, the phrasing has been borrowed from thermodynamics. So these theorems created a great deal of buzz. And these theorems were proved during a summer school like this. Okay? This was in the Swiss Alps, in the French Alps rather, a place called Les Houches, where there used to be regular summer schools. Two very distinguished physicists, husband and wife, De Wit and De Wit, they started these summer schools in the 1950s. They used to just carry potatoes and other things up there, and then people will meet, they will talk physics for 2 weeks and cook and have a great time, and meanwhile do physics. And so you people must discuss among yourselves. That's why I'm saying this. All these theorems were proved during one of those leisure schools, as indeed what I'm about to say now. When quasars were discovered, as I said, Ginsberg was one of the persons who was wondering what could possibly be the central engine. He came to the idea that it could be a supermassive star, and then Chandrasekhar said this could collapse. And then he asked, but look, if a supermassive star had a magnetic field, will the black hole have a magnetic field? And then he produced a simple but beautiful physical argument to say that no, the black hole will not have a magnetic field. Then Zeldovich asked the question, suppose the star had a little mountain on it, will the black hole have a little pimple on it? Or if suppose the star was a cube, will the black hole be a cube? He said, no, the black hole will be a perfect sphere. These were conjectures. These were conjectures by very powerful minds, but they had to be proved. So, a whole lot of brilliant young people, tremendously gifted in mathematical skills, got to work on this. And they proved a series of theorems. Again, these theorems came in summer schools. And these theorems go under the name of no-hair theorems. These are all very important in the context of final merger of black holes. Okay? That's why I'm telling you this. The first theorem was proved by Werner Israel in 1968, that a neutral and non-rotating black hole is uniquely characterized by its mass. Everything else is radiated away as gravitational radiation. Then the next theorem was proved by Stephen Hawking 2 years later, that all stationary black holes are axially symmetric. Okay. And then came the final theorem by Carter, Hawking, and Israel in 1972, that all charged rotating black holes, if it should be charged, are uniquely characterized by their mass charge, and angular momentum. So if you haven't written down, it's again here. That's why I moved fast. Okay. So black holes are uniquely characterized by their mass, charge, and angular momentum. Now this is an exact theorem, as indeed the other theorems are, and it is profoundly important, obviously. Because please remember, the whole of the 20th century was about finding new conservation laws and particles associated with breaking symmetries. Okay? We had isotopic spin, we had lepton number, baryon number, strangeness. Suddenly, as John Wheeler said, if you made a black hole out of television sets, you made another black hole out of cars, you made another black hole out of electrons and neutrinos, you can't tell the difference. All you know about a black hole is its mass and angular momentum. Charge is not relevant in an astronomical context, but mathematically, charge is also allowed. Okay? So, does a black hole violate all the laws of physics that we learned in the 20th century? No one is quite saying that. So, what people say is that almost all the conservation laws are transcended by black holes. In other words, there is no way for you, by long-range experiments, to deduce these properties of a black hole. So there is a genuine loss of information. Nobody is saying that these laws are violated. Nobody is saying they are not violated, but they are certainly not saying they are violated. Okay? So the safe bet is to say that these laws are transcended. So this theorem and Kerr's metric provoked this reaction from Chandrasekhar. In my entire scientific life, the most shattering experience has been the realization that an exact solution of Einstein's equation, the Kerr metric, provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. Every black hole in the universe can be described exactly by this, right? We cannot even give an exact description of the helium atom, right? All right. And then came the quantum twist, as I like to call it. A young student of John Wheeler in Princeton, Bekenstein, argued that black holes must have enormous entropy, 10 to the power 79 for a 10 solar mass black hole. He argued that not only it must have an entropy, that the entropy must be proportional to the surface area. In other words, the entropy of a black hole should be proportional to the surface area of the black hole, 4 pi r Schwarzschild squared. Now, from purely dimensional arguments, you can show that the constant of proportionality has to be Boltzmann's constant, velocity of light, Newton's constant, and Planck's constant. This caused a lot of consternation because you are dealing with classical thermodynamics and you are dealing with classical gravity. What business has Planck's constant got to make an appearance in this formula? So it reminded people of 1900 when Max Planck was trying to construct the black body radiation spectrum, where he was trying to unify classical radiation theory with classical thermodynamics. You'll remember that's where this constant first appeared. So people wondered whether Bekenstein's suggestion is signaling some very major breakthrough in gravitation. But Hawking was very skeptical of Bekenstein. They had a series of arguments about it. Hawking's point was that a black hole cannot have entropy because only bodies at finite temperature can have entropy. Now, classical black hole absorbs everything, it doesn't emit anything, so it's a perfect sink. And according to thermodynamics, the only perfect sink is that at absolute zero of temperature. It doesn't emit anything, it can only absorb something. So a black hole must be at zero temperature, therefore it cannot have entropy. Although the theorem that he and others proved, the first law of black hole mechanics, did suggest that the area of the black hole is second law suggested area is perhaps proportional to the entropy. Then in 1973, late 1973, Hawking went to Moscow to meet Zeldovich and discuss with him. Everybody went. Everybody west of Suez went to Moscow to talk to Zeldovich because Zeldovich wasn't allowed to travel outside. So Zeldovich asked Hawking the following question. He said, look, if I take a metal sphere and I spin it, it will emit electromagnetic radiation. Virtual particles that pop out of vacuum can materialize, can become real by extracting energy from the rotating sphere. Indeed, in 1970 and 72, Zeldovich had published two very extraordinarily brilliant papers. He showed, first of all, he was talking about a phenomenon which is known as superradiance. This superradiance is a phenomenon that is borrowed from superradiance in atoms. Superradiance is a phenomena where waves of a certain frequencies incident on a rotating black hole are scattered back with greater intensity. And of course, this is not a violation of anything because you're just extracting rotational energy from the black hole. But Zeldovich's point was that in a particle picture, this corresponded to stimulated emission of particles in that particular mode. I send in n particles in that mode, what comes out is greater than n. So stimulated emission, like in a laser or a maser. And then he remembered Einstein, 1917. You remember Einstein said that whenever there is stimulated emission, there must be spontaneous emission. So let's examine this statement properly. Right? We'll come back to this. That's why I think that slide is missing. I probably have displaced it. So having said, recall these two papers of his to Stephen Hawking, he asked Hawking the following question. So Zeldovich was very clear in his mind that a rotating black hole will spontaneously emit particles. Forget not just the scattering, spontaneously emit particles. But it's a rotating black hole. In principle, those particles could come at the expense of rotational energy. The question he asked him was, will a non-rotating black hole radiate? And then, let me now state the reason why he asked that. You remember in 1917, Einstein introduced the idea that in addition to stimulated absorption and stimulated emission, there must be spontaneous emission. And it is this interplay between stimulated emission, spontaneous emission, and spontaneous absorption that results in the spectrum of black body radiation being Planck's law. So Einstein gave the first derivation of Planck's law, for which he had to introduce spontaneous emission. So whenever there is stimulated emission, there must be spontaneous emission. Okay, so that was Zeldovich's point. So then, of course, as you all know, a few months later, Hawking made this remarkable discovery that a non-rotating black hole will radiate. It will emit particles and radiation in all modes, not just the analog of the super radiant mode, because this is not a rotating black hole anymore. It emits in all. But most surprisingly, it emitted radiation and particles as though it was an ordinary body with a temperature T, which is proportional to the surface gravity kappa. You remember from the first law of black hole mechanics, we had identified the temperature of a black hole with its surface gravity. And what he found was that the number of particles emitted in a certain mode with a frequency omega is 1 over e to the power 2 pi omega by kappa minus 1. And there is the black body radiation formula. So you see the temperature is indeed the analog of surface gravity kappa. But more importantly, Hawking found that the probability of emission from a black hole is related to the probability of absorption by a black hole by this principle of detailed balance factor, e to the power omega over kappa. And this is what Einstein derived in 1917. Probability of emission is related to absorption by e to the power minus h nu over kt. Now, important thing to appreciate is that because you're dealing with a non-rotating black hole, the emission of radiation will result necessarily in the decrease in the mass of the black hole. It has to come at the expense of the mass of the black hole. There is nothing else. But Hawking didn't quite like this result because it was intuitively not acceptable to him. He tried very hard to make it go away, but it wouldn't go away. And others calculated it and found that they got the same result. And so what finally convinced Hawking was that it was of a thermal nature. What do I mean by that? Recall that when matter and radiation come to thermodynamic equilibrium, as I said 2 days ago during our tutorial, radiation loses all its memory. How it was produced, what was its frequency, what was the direction, what was the polarization. When it comes out, it remembers only one property, namely the temperature of the body. Similarly, Hawking radiation, we have lost all information about what went into the black hole, no hair theorem. So the only thing the body remembers is the analog of temperature is the mass of the black hole. Okay. So Hawking felt that the thermal nature of the radiation emitted by a body reflects the loss of information that Bekenstein was talking about, the large entropy. Now, this is dealt with. Now, as you all know, that this temperature of this black body, a black hole, can be written in these units, 10 to the power minus 6, m sun by the mass of the black hole. Therefore, it's really not relevant. These black holes of a solar mass is still at a temperature 1,000,000 times less than the cosmic microwave background temperature. So it's only relevant for black holes which were possibly produced in the very early universe, in the grand unification era or even before that, whose masses were of the order of 10 to the power 17 or 18 grams and whose size would be the size of a proton. Their temperatures will be enormously high. But the question is not that. The question is, if such black holes were produced in the early universe, they will evaporate away. And what will remain is a naked singularity. So it really doesn't matter whether the singularity was produced outside the horizon or inside the horizon. The horizon is gone now. So there is the singularity. And that poses serious problems to physics because you have to ask, if there is a singularity in space-time, you don't know what went into it. So you don't have a description of the singularity. You don't have a description of the interaction of the singularity, any singularity. That's why physicists don't like singularity. So Hawking's point was that a naked singularity would introduce an additional element of uncertainty in physics over and above Heisenberg's uncertainty principle. Because if you remember, since the particles are emitted by a black hole come from some region, you cannot say it came from there or there or there, it comes from a certain region. He cannot predict, not only cannot predict precisely the position or the momentum or a linear combination of it a la Heisenberg, you can't even say that. You can only say that there is a probability that certain particles will be emitted, like in black body radiation. So that's why in his famous Scientific American article, he famously said, Einstein was doubly wrong. Einstein said God does not play dice. God not only plays dice, he throws them in places where we cannot see. Now, all this is not particularly relevant for gravitational radiation from black holes and so on, but what is relevant are the no-hair theorems because when two black holes finally merge, you have to ask whether the signature of the gravitational radiation has anything further to say apart from just mass and angular momentum of the black hole. Yesterday, after the second lecture, I was having a discussion with Professor Iyer here, and some remarks he made about the three detections that have taken place so far prompted me to end this lecture on the following note. I will read it out for you. Chandrasekhar, black holes are macroscopic objects with masses varying from a few solar masses to millions of solar masses. To the extent they may be considered as stationary and isolated, to that extent, they are all, every single one of them, described exactly by the Kerr solution. This is the only instance we have of an exact description of a macroscopic object. Macroscopic objects, as we see them all around us, are governed by a variety of forces, derived from a variety of approximations to a variety of physical theories. In contrast, the only elements in the construction of black holes are our basic concepts of space and time. They are, thus, almost by definition, the most perfect macroscopic objects there are in the universe. And since the general theory of relativity provides a single, unique two-parameter family of solutions for the description, they are thus the simplest objects as well. Okay. So on that note, that's the right note to end this lecture. If there are some questions, either I or some expert sitting here can answer this. Thank you. Yes. If it still has, till, till it radiates away all the angular momentum, it has angular momentum. So you need the description requires angular momentum, right? Gravitational waves are time-dependent perturbations of the space-time itself. So you can't ask gravitational waves and say, well, are you carrying lepton number or strangeness quantum number? Right? It's a profoundly surprising theorem, this no-hair theorem. Right? People, I have not followed this simply because I am not able to understand these arguments. But from what I can understand, there is a heated debate going on. Hawking is trying to retract some of his earlier claims. He thinks that information can be retrieved. Others are saying this is not possible. So I don't think the dust has settled down. Okay. So maybe during the coffee break you can talk to Dr. Iyer. He can tell you probably some more. I've tried to follow this. It's just impossible for me to understand these arguments. Mathematically, it's so complex. Finally, there is no clear statement at the end, which I can, in English language, which I can hope to understand. It hasn't reached that stage yet. The arguments are going. Obviously, it's of great importance. It's of very great importance. For example, Professor Spenta Vadia here feels that there is a major conflict between quantum mechanics and black hole physics. This is one reason that very learned physicists don't believe in black holes. These are not people who confuse coordinate singularity with real singularity. They're very serious people like Feldman and others. And the reason has to do with this kind of a conflict. Okay. Quantum mechanics, pure states cannot become mixed states. Right? Yeah. So, pure states became mixed states only once in our history. That is when black body radiation was understood. We finally know that what was created were all pure states. Finally, there's been a loss of information, which, but then that was the beginning of a great revolution, right? Planck's discovery was the forerunner to the quantum revolution. So maybe one is going to witness, you people are privileged to you'll be around to witness this revolution. But what it is going to be, we cannot anticipate at this stage. There is a serious conflict, there is no doubt about that. And that conflict has nothing to do with quantizing gravity at the Planck length. The Hawking radiation has posed another serious conflict, okay, already at this scale. So believe very serious physicists. Okay. Yes, are there any other questions? Yes? That would always remain, yes. Isn't it? It can radiate away energy, but it cannot radiate away charge, isn't it? Radiation doesn't come at the expense of charge, isn't it? So, because it's not monopole radiation, it's higher order, right? So I don't know of any way a black hole can get rid of its mass. But you know, but astronomically, if you talk of black holes in the realm of astronomy, there's going to be no significant charge because strong electrostatic forces will be forbidden in macroscopic bodies. So it's probably not. But mathematically charged black holes are very exciting objects. Okay. Thank you.